Imagine you spend years training for the most dangerous job in human history. You study every failure, every crack, every system that could kill you. You sit in the briefing rooms. You see the photographs of the heat shield that broke apart on the last mission. You ask the engineers the hard questions and they give you honest answers. And then you climb in anyway. That is not recklessness. That is not blind courage. That is something far more interesting and far more human. 4 astronauts are preparing to travel farther from Earth than any living person has ever been. Not to a space station 400 kilometers up where you can still see city lights below you, but to the moon, 385,000 kilometers away, where Earth shrinks to a pale blue dot in the window. And the only thing standing between 4 human bodies and the vacuum of space is engineering, mathematics, and a heat shield that cracked the last time it was used. Here's the question worth asking. When you know exactly how something can kill you and you go anyway, what is actually happening inside the human mind? Subscribe if you want to find out. Now, let's begin. December 7, 1972, Apollo 17 lifts off from Kennedy Space Center. It is the last time in human history that a crewed spacecraft leaves the gravitational neighborhood of Earth and points itself at the moon. Commander Gene Cernan steps off the lunar surface, climbs back into the ascent module, and that is it. The door closes, and for 53 years it stays closed. Think about what 53 years actually means. An entire generation was born, grew up, had children of their own, and watched those children grow up, all within the gap between that last footprint on the moon and this mission. Space exploration did not stop. The International Space Station has had continuous human presence since 2000. Hundreds of astronauts have lived and worked in orbit. But here is the critical detail most people miss. Every single one of them stayed close. The ISS orbits at roughly 400 kilometers above Earth's surface. Low Earth orbit, still inside the protective bubble of Earth's magnetic field, still close enough that on a clear night, you can track it with your naked eye from the ground. The moon is 385,000 kilometers away. That is not a bigger number. That is a different category entirely. Swimming laps in a pool versus swimming out into the open ocean past the point where you can no longer see the shore, with no boat nearby and no way back except your own body and whatever you brought with you. Artemis II is the first time since 1972 that humans are swimming into the ocean. Let's talk about what the fear is actually made of, not the abstract cinematic fear of space. The specific documented engineering level fear that comes from knowing exactly what went wrong before and not being entirely certain it will not go wrong again. Start with the heat shield. When Artemis I returned to Earth in December 2022, it looked like a success from the outside. The capsule splashed down safely. Cabin temperatures stayed within design limits. The mission was declared nominal. Then the engineers got close and started inspecting the heat shield. What they found was not catastrophic damage. It was something more unsettling than that. Over 100 locations where the ablative material, a substance called avcoat, had cracked and broken away in irregular, unpredictable chunks. Not the smooth, controlled erosion the material was designed to produce, jagged, unplanned loss. 4 separation bolts embedded in the shield had partially melted through their thermal barriers, leaving deep gouges in the surface. The investigation took nearly 2 years. The root cause came down to a technique called skip re-entry, where the capsule dips into the atmosphere, bounces back out into space, then re-enters a second time. That pause between atmospheric contacts allowed heat to accumulate inside the shield material without letting it ablate properly. Pressure built up. The material cracked and blew apart from the inside. For Artemis II, NASA changed the trajectory, a steeper, more direct entry with no skip. The trade-off is higher deceleration forces on the crew during those final minutes. The shield itself, the same avcoat material, was not redesigned. The fix is a different flight path tested in models and simulations, but never yet tested with 4 human beings inside the capsule. That is the first layer of fear. Here's the second. Beyond the protection of Earth's magnetic field, the crew of Artemis II will be exposed to 2 categories of radiation that the International Space Station almost entirely shields against. Galactic cosmic rays, high-energy particles streaming in from outside our solar system pass through spacecraft walls and human tissue with very little resistance. Solar particle events, sudden bursts of radiation from the sun, can deliver dangerous doses in hours. NASA has shielded areas inside the Orion capsule where the crew can shelter during a solar storm. The most protected location with the most material between the astronauts and the incoming radiation is the area near the toilet, That is not a metaphor. That is the actual contingency plan. The third layer of fear is the one that does not appear in engineering documents. 4 adults, 330 cubic feet of living space, 10 days. No rescue vehicle within any practical range. A communication delay with Houston that, while only about 1.3 seconds each way, is just enough to make a real-time conversation feel slightly wrong, slightly off, slightly like the ground beneath you is not quite solid. Researchers who study isolated and confined environments have documented what they call the third quarter phenomenon, a pattern where psychological stress and interpersonal tension peak during the middle to late stage of a mission, precisely when the initial excitement has faded and the end still feels distant. And Artemis II is short enough that this may not fully develop, but the crew will be operating in conditions no simulation can perfectly replicate, collecting data on their own psychological responses in real time in a place where no human has been in over half a century. The fear is not irrational. The fear is made of cracked heat shields, invisible radiation, and the specific loneliness of being farther from every other living thing than any human alive has ever been. And they are going anyway. Now turn the lens around, because the same mission that carries every risk described in the previous section also carries something that no amount of training, no simulation, no virtual reality environment has ever been able to fully replicate. Something that astronauts who have experienced even a fraction of it consistently describe as the most transformative moment of their lives. It has a name. Researchers call it the overview effect. The term was coined by writer Frank White in 1987 after conducting extensive interviews with astronauts about their psychological experience in space, but it was not White's invention. It was a pattern he noticed across dozens of independent accounts from people who had no reason to describe their experience in the same way, using the same language, arriving at the same conclusion. When human beings see Earth from space, something shifts in the architecture of how they understand themselves and the world they came from. This is not poetry. This is neuroscience. Research into the cognitive and emotional experience of awe, particularly the work of psychologist Dasha Keltner at the University of California, Berkeley, has shown that encounters with things vastly larger than ourselves trigger a specific and measurable response in the brain. The default mode network, the system responsible for self-referential thinking, the constant internal narration of who you are and where you fit becomes quieter. The boundaries between self and environment soften. What people report is not happiness exactly. It is something closer to the sudden, overwhelming sense that the categories they had been using to organize reality are too small for what they are looking at. Edgar Mitchell, who walked on the moon during Apollo 14, described the moment of looking back at Earth as an instant global consciousness. He saw the planet hanging in the blackness and understood, not intellectually but physically, that everything he had ever known was contained in that single fragile object. Mitchell was careful to distinguish this from a religious experience. He described it as a data experience. The data simply arrived at a scale his previous frameworks could not process. Now consider what the crew of Artemis II will see that Mitchell did not. When Orion swings behind the moon on its closest approach, the 4 astronauts will be 685,000 kilometers from Earth. At that distance, our entire planet fits comfortably within the frame of a small window. Every human being who has ever lived, every war ever fought, every city ever built, every person you have ever loved, reduced to a point of pale blue light against absolute darkness. And then the capsule moves behind the moon, and even that disappears. For approximately 30 minutes, the crew of Artemis II will have no line of sight to Earth whatsoever. No signal from Houston, no telemetry, no voices. Just 4 people and the lunar surface filling one side of their windows and the infinite darkness of deep space filling the other. This will be, by any measurable definition, the most isolated group of human beings in the history of the species. And here is what the data on awe consistently shows. Isolation at that scale does not produce only fear. It produces a simultaneous expansion of perspective that people who have experienced it almost universally describe as the closest thing to clarity they have ever felt. You have never seen your planet. Not really. You have seen pieces of it. These 4 people are about to see the whole thing at once and then watch it vanish. Here's the question that the previous 2 sections were building toward. How do both of those things exist inside the same person at the same moment without one destroying the other? Start with the neuroscience, because the answer begins there. Research on the human threat response system has revealed something that seems counterintuitive at first. The brain regions most activated by fear and the brain regions most activated by awe are not opposites. They are neighbors. The amygdala, the structure most associated with processing danger and triggering the fight or flight response, is also heavily involved in processing experiences of overwhelming magnitude, beauty, and scale. What neuroscientists sometimes call the threat-reward duality describes a state in which the brain simultaneously registers something as potentially dangerous and as deeply compelling without resolving that tension into a single clean response. Think about standing at the edge of the Grand Canyon for the first time. Your body registers the drop. Your pulse rises. Your instincts send a quiet signal to step back. And at the exact same moment, you cannot look away. The scale of it pulls you forward even as biology tells you to retreat. You do not experience the fear and then the awe in sequence. You experience them as a single fused sensation that has no clean name in everyday language. Now scale that up by several orders of magnitude. The philosopher Immanuel Kant wrote about a concept he called the sublime, the experience of encountering something so vast and so powerful that it simultaneously overwhelms the senses and elevates the mind. Kant argued that the sublime was not comfortable. It was not pleasant in the way that beauty is pleasant. It was confrontational. It forced the person experiencing it to reckon with their own smallness and, paradoxically, to feel enlarged by that reckoning. The crew of Artemis II is flying directly into the Kantian sublime, and they are doing it with full, informed awareness of every technical risk attached to the journey. This is where the analysis becomes genuinely interesting. Psychologist Mihaly Csikszentmihalyi spent decades studying the mental states that humans describe as their most meaningful and alive. What he found was that the experiences people remember most vividly, the ones they describe as feeling most fully themselves, occur almost exclusively in conditions where the level of challenge and the level of personal capability are both pushed to their absolute maximum simultaneously. He called this state flow, not comfort, not safety, the razor's edge where everything you have is exactly what the moment requires and nothing is left over. No simulation produces flow. Comfort does not produce flow. The condition that produces it is precisely the condition these 4 astronauts are voluntarily entering. And here is the direct implication for you watching this from wherever you are right now. The same neurological architecture that allows Reed Wiseman to sit on top of 8.8 million pounds of thrust and feel something other than pure terror is present in your brain. The capacity for awe and fear to coexist, to fuse into something that propels rather than paralyzes, is not a special trait belonging to astronauts. It is the trait that carried every ancestor you have ever had through every moment of genuine uncertainty they survived. Artemis II is not an exception to human nature. It is human nature expressed at the most extreme scale currently available to our species. Here is what we do not know. And in the context of this mission, what we do not know matters as much as what we do. Start with radiation. NASA's current models for predicting radiation exposure in cislunar space are built on 3 sources of data. First, measurements from astronauts aboard the International Space Station, who are still largely protected by Earth's magnetic field. Second, the readings collected by the uncrewed Artemis I capsule during its lunar mission in 2022, which carried radiation sensors but no human biology to measure against. Third, computational models extrapolated from medical radiation research conducted entirely on Earth. None of these is the same as a living human being spending 10 days in deep space. What Artemis II will produce for the first time since the Apollo era is actual biological data from actual human bodies moving through the radiation environment beyond Earth's protective field. The crew will wear personal dosimeters throughout the mission. Their health will be monitored closely in the months and years following their return. The data they generate will be, in a very literal sense, irreplaceable. No model, however sophisticated, is a substitute for the measurement. This is not a reassuring fact. It is an honest one. The second roadblock is psychological, and it is less discussed than the engineering challenges, but arguably just as significant. The entire body of long-duration spaceflight psychology research is built on data from the International Space Station, where astronauts can video call their families with near real-time connection, where resupply missions arrive regularly, and where Earth is always visible and close. That environment is fundamentally different from cislunar space in ways that matter psychologically. At lunar distances, the communication delay is small but perceptible. Earth is not a comforting presence filling the window. It is a small, distant object. The psychological framework we currently have for understanding human behavior in space was not built for this environment. Artemis II will begin to build that framework. But on this mission, the crew will be operating partially beyond the edge of what our existing research can reliably predict. That is the honest scientific position. Not alarm, not dismissal. Acknowledgement that some of the most important data from this mission does not exist yet and will not exist until the mission itself creates it. It would be intellectually dishonest to present this mission without acknowledging the serious case against it. The criticism is not fringe. Respected scientists, engineers, and policy analysts have argued that the Artemis program, with its estimated total cost approaching $93 billion through 2025, represents a deeply inefficient allocation of resources. The core of the argument is straightforward. Robotic missions can go where humans cannot, stay longer than humans can, and do so without risking human lives or requiring the enormous engineering overhead that keeping 4 people alive in deep space demands. The scientific return per dollar, critics argue, is substantially higher without the human element. There is data supporting this position. The James Webb Space Telescope, at a total cost of approximately $10 billion, has fundamentally transformed our understanding of the early universe. Mars rovers have operated for years collecting geological data no crewed mission has yet matched. But here is where the counter-argument finds its footing. There is a category of data that robotic systems cannot generate. Human physiological response to deep space radiation, human psychological adaptation to genuine isolation beyond Earth's protective field, human judgment in conditions no simulation has fully replicated. Every crewed mission beyond low Earth orbit produces knowledge that cannot be extracted from any machine we have yet built. That is not sentiment. That is a gap in our current scientific instrumentation that only human presence can fill. What happens next depends almost entirely on what Artemis II brings back. If the heat shield performs as the revised trajectory models predict, the path toward Artemis III opens. That mission, currently targeted for no earlier than 2027, would return humans to the lunar surface for the first time since 1972. The specific landing site is the lunar South Pole, a region of permanent shadow where water ice is believed to exist in quantities that could support long-term human presence. Everything about that mission depends on the engineering validation that only Artemis II can provide. Beyond the moon, the data collected on this mission will directly shape the design parameters of every crewed vehicle currently being developed for Mars. Radiation exposure profiles, psychological performance metrics, physiological adaptation data. These are the inputs that determine whether a Mars mission is a calculated risk or an unacceptable one. Artemis II is, in a meaningful sense, the first real data point in humanity's preparation for interplanetary travel. And here is the question worth sitting with. If we can design a vehicle capable of carrying 4 people to the moon and back, absorbing every risk that entails and bringing them home, what does that tell us about the actual boundaries of human exploration? Are those boundaries defined by technology, by resources, or by something more fundamental in how our species decides what is worth risking everything for? Artemis II will not answer that question, but it will move us measurably closer to understanding it. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are not going because they are fearless. The evidence suggests the opposite is true. They are going with full knowledge of cracked heat shields, invisible radiation, and the specific documented loneliness of deep space. They have seen every photograph of every failure. They have sat in every briefing. They have asked every hard question. And they have decided that what is on the other side of that fear is worth the crossing. There is something in that decision that belongs to all of us. Not because we are all capable of climbing into a rocket, but because the neurological architecture that makes that decision possible is the same architecture you are running right now. The capacity to hold fear and awe simultaneously, to feel the weight of genuine risk and move toward it anyway, is not a mutation that appeared in astronaut training programs. It is the oldest software our species has. It is what carried the first humans across land bridges into unknown continents, across open oceans in boats held together by belief as much as engineering. Artemis II is the latest expression of something very old. The universe does not offer safety. It offers distance and the possibility of what lies across it. These 4 people have chosen the distance. The only question the rest of us need to answer is what we are choosing.